25 years ago, I solved AGI, or artificial general intelligence, with a human brain emulation model called Patom theory. I explained the revolutionary theory in 1999 for Australian radio. The ABC had a great show called the Occam's Razor program. The solution to how our brain works enables all our brain's capabilities. And rather than the computational system that has been assumed since the 1940s, observations of brain function show an alternative. With templates to recognize vision, for example, we can identify shapes. With coordinates in a computational model, however, we need to convert the coordinates into a visual representation using math. There are limitations to a math based model, and anyway, who said we need computations? The main difference from the computational model is the elimination of encoded data and the need for a program. Both of those issues have been very problematic to emulate brains because brains don't seem to have either the encoded data or the programs. As proposed in 1956 at the Dartmouth conference, an AI system should learn and work like people's brains do. Machine learning, in contrast, is not human like. For example, many systems today start with humans labeling large data sets, while people just learn the names of things through experience, which is far superior. When we see, specific brain regions are involved just as our eyes are. When we hear, similarly, specific brain regions are involved as well as our ears. When we touch something, specific brain regions are involved, and when we move, specific brain regions control it. In language, speech requires a particular region, Broca's area, and when we comprehend language, another specific region or regions are involved, like Wernicke's area. Long-term memory in particular requires specific regions to facilitate, and I could go on and on describing these specialized regions. Interestingly, individuals differ in the specifics of the regions. This plasticity, as it's called, is explained by a region model in which patterns are stored since the initial pattern is stored where first recognized, not encoded and sent, and then signaled to other parts of the brain. Not only do our senses and motor control come from a particular brain region, but they're joined together by common regions. Patom theory aligns with observations. Rather than intelligence and a program controlling our brain, the brain stores and uses hierarchical patterns in a combinatorial manner. This is completely different from today's statistical approach to AI used in deep learning and large language models. For simplicity, let's call this new model, deep symbolics, and I'll talk much more about deep symbolics in future programs. When people ask about today's generative AI systems for enterprise, I tend to point out the harsh truths. Today, the large language models cost a lot. While the numbers are usually unpublished, $100 million has been mentioned. That's just for the initial training. Some are more expensive, some are less, but it's significant. There are additional costs proposed to deal with the errors it generates, such as systems called RAG, fine-tuning, and perhaps even agents and legacy integrations. This leads to potential maintenance costs for new releases where new systems aren't backwards compatible, needing the entire project to be redone from scratch in the future. This leads to potential maintenance costs for new releases in the future where new systems aren't backwards compatible, needing the entire project to be redone from scratch. That sounds like a nightmare. And rather than each enterprise servicing these costs, a better model would provide meaning and necessary language as part of the core language platform. That's the proposal that I make. Testing language separately to meaning-based knowledge would massively reduce the cost of a language system and ensure knowledge needs only be stored once. Something like 40 years ago, my science degree from the University of Sydney included computer science and pure math as my focus. My goal was to be like Scotty from Star Trek one day and become a computer engineer. I achieved that goal a couple of years later, thankfully. But during my studies, I was zapped by this compulsion to create intelligent machines. My computer science lecturer, Professor Judy Kay, said we were unlikely to ever be able to replicate human brains because they are too complex. That was some amazing motivation, Professor. Thank you. And that set me on a path that still continues for me to this day. In the year 2000, what later became known as AGI was called strong AI. In strong AI, the system emulates a human in every way: motor control, sensory perception, conversation, and even consciousness. And while we don't need consciousness, the others are still very important to produce intelligent machines. Now, while in science there's no reason to ever limit the goal, in engineering and business, moving the goalpost may make a simpler problem solvable without needing to solve the original one. It's a bit tricky. And today, AGI is being watered down to avoid the difficult aspects that have limited progress over the past 70 years. The watered down model gives a simpler path to what's falsely called AGI. But the reason to pursue strong AI, the original goal, is simple. It enables the killer AI apps that have been stuck with little progress for the last 10 to 20 years. What's strong AI? Well, strong AI emulates a human brain. Only humans today can speak one or more languages, learn gymnastics, and navigate using language. Why should we bother with the pursuit of strong AI? In my recent book, I point out how the world is ready to change dramatically as the result of AI that can emulate brains. Stalled killer AI applications include human level only skills: speech recognition, translation between languages, understanding and conversation, and teaching language using that language. Imagine how you could work with devices if they understood you as a person does. Conversation is far better than commands, but we need speech recognition to work at human level. Imagine if machines understood what you said and correctly translated it into another language of your choice. And imagine if you wanted to learn another language and a machine accurately helped you with ongoing feedback. My biggest goal is to facilitate the use of meaning as an interlingua. If you know what that means, it's the go between the language and another representation that's ideally lossless. You could buy a newspaper and immediately read it in your choice of language if it were stored as lossless meaning, as that interlingua. It's possible to do this within a short time frame if we want to pursue it. The reason to solve these problems is that it would revolutionize our world. Devices would do what we want just by talking to them. We could communicate with anyone as our devices translate to them. At the core of these miracles is human brain emulation that we've already demonstrated in software. If you're interested in seeing AGI come to fruition, keep following me. We've started a project to use my language understanding platform in conjunction with a world expert in language learning who has been teaching English to Mandarin speakers for over 15 years. Learning a language is best done by aligning this approach and how our brain works, of course, and in the coming weeks, I'll explain more here and in my Substack. It's very exciting because the use of lossless knowledge in a language system ushers in the next generation of AI in a way that immediately helps learners. This works just like a parent would do, but this time a robot, the speech genie, will automate the help. That's it for today. And if you want to understand the background of Patom theory, don't forget to get a copy of my latest book from Amazon. And remember, tell your friends to tune in as we turn on the next generation of AI and exploit the sciences of brains and language. Bye for now.